All right, welcome back to the Institute. In today's lecture, we are basically going to understand the concept behind inductive principles or mathematical induction. But before we begin, we have to understand the intuitive concept behind induction before we move on to the mathematical concept. Right. So I want to ask you this question. Do you know what dominoes are? Or do you know what a domino is? Of course, you must know it because you have been playing game all the time at your leisure times, right? So leave your answer at the comment section. What is a domino? 1 minute. All right. So basically, a domino or dominoes are small rectangular tiles, okay? They are small rectangular tiles and they are usually used in games, right? They are usually used in games. Now, each tile is like divided into, let's say, squares, okay? It's divided into squares and each square has dots, okay? Each square has a dot like a die. So this is the square and it has a dot. So something like a die, right? Or a dice. Nice. So you know that dice showing what? It shows from 0 to what? 6, right? Good. Now we understand the concept of dominoes, right? Now let's come to some explanation in mathematics, okay? Now imagine um, you have a line of dominoes, okay? You have a line of dominoes. Now those dominoes, they are standing upright, okay? They are standing upright. So we are saying that this should be a domino and this is standing upright, okay? Now, if you push the first one, okay, this is the first one and it is standing upright. So let's say there is another one down here, okay? There is another one down here. There is another one here too, okay? And you push the first one. Now, each domino or each die is placed so that when one falls, it pushes the next one, right? So you see the way I place this one. If this one falls, automatically this one will come down as well. This one, that is the assumption behind it. Now, each one is placed so that if the first one falls, the next one would also follow. And eventually, all of them will fall. Now, let's think about the mathematical induction, right? So in the mathematical induction, we have 3 stages or we have 3 processes that we undergo for us to be able to prove that this thing is valid using mathematical induction. So the first stage is the base case, right? So step one is the base case. The base case. In that case, you say that n should be equal to what? 1. The small n should be equal to what? 1. Okay? Okay, so that is where you show that the the statement is what? True. Like pushing the first domino down, right? So you show that if you push the first domino down, it will fall, right? And that is where you say that n is equal to what? 1. That is the base case. So you are showing that if you push the first die down, if you push the first die, according to how you've arranged it, it will fall, right? So that is the base case. Now the second stage, which is the step 2, which is the inductive hypothesis. Inductive hypothesis. That is where you try to do assumption, right? You do assumption and see that, and say that if n is equal to 1 is falling, then if you replace n with k, then that one too will fall. So in that instant, we do what we call assumption, right? So we say that assuming n is equal to 1, then the statement will be what? True. Assuming the statement n is equal to what? K, then the statement will be what? True. So in that instant, we say that assume that the statement is true when n is equal to what? K. So that is the second stage. And then the final stage, which is the step 3, is your inductive step, right? So in here, you are going to, based on this assumption, to prove this. So if you are saying that n is equal to k will be true, you are assuming, right? Then n equals 1, n equals k plus 1 should also what? Work, right? So that is the third stage, okay? Now, let's take a problem, a very nice problem, and then use it to solve this particular or understand this concept, right? So this is a very nice problem that we are going to use. Very nice problem, right? So the question goes this way. Prove by mathematical induction that for all n, this is a number, right? So this can be 1, 2, 3, 4, whatever, right? So for all n, that belongs to what? Natural numbers, right? That belongs to what? Natural numbers. 7 to the power n minus 1 is divisible by what? 6. That is, we want to show that 6 divides 7 to the n minus 1. Okay, so we are going to begin with the process. So you know the 3 processes. You know that step 1, which is the base case, n should be equal to what? 1. So this is very, very important. Please always try to write it, okay? Always try to write it. So step 1, which is the base case, n should be equal to what? 1. So we are going to lift this statement and then substitute 1 in place of what? N. So we say that 6 given 7 to the n minus 1 is equal to 7 on 7 to the power 1 minus 1. And this is equal to 7 divides 7 minus 1, right? And this is equal to 7. 7 minus 1 is what? 6, right? So we have 6 here. So this statement, 6 on 6, we are not interested to know the number, right? we are not interested to know the exact number that this one will give us, right? But rather, we want to know if this expression is going to give us an integer. Take it again. If you get to this stage, don't be tempted to write 6 over 6 is equal to what? 1, right? We are not interested in the division. We want to know if this right here, the result will give us what? An integer. And we know that 6 on 6 is 1, right? It's 1. And we know that 1 is what? An integer. Okay? 1 is an integer. So we say that the statement is what? True. So the base case is what? Valid. So the base case is what? Or the base case holds. And that is true, right? So let me take it again. If you get to this point, don't be tempted to divide 6 on 6 and write what? 1. It is never true. We are not interested, or we don't want to know what it will give us or the output. We want to know if this statement right here, the result is going to give us an integer. If it is not an integer, then the base case will not work. But if it is an integer, then the base case will work, right? So now we know that the base case is valid. Now let's move on to the second step, which is the inductive hypothesis. So step 2, inductive hypothesis. Inductive hypothesis. So in this step, this is where we do assumption, right? So like I said in the game, you push the very first game, it fell, right? And you believe that the way you arrange the games, because the first one fell, you are assuming that the second one too will fall, right? So let's say I have something like this, right? I have something like this. I push this one fell. I'm assuming that if I push this one too will fall, right? So that is the inductive hypothesis. So that is where you assume that the statement is what? True when n is equal to what? K. So now you are going to say that, so this assumption is very, very important, okay? It's very important. So assume that the statement is true when n is equal to what? K, right? So you are assuming that the statement will still be true if n is equal to what? K. So we are going to substitute k in place of what? N. So we have 7 to the k minus 1 here. And we know that in modulo, this statement right here, in other words, it is a modulo arithmetic language. Modulo arithmetic language. So this means that it is 7 to the k equivalent to 1 modulo 6, right? So this actually means that 7 to the k is equal to 6m plus 1, right? 6m plus 1, right? For some m belonging to what? Integers, right? For some m belonging to what? Integers, right? So that is the inductive hypothesis. That is the inductive hypothesis. So now we are good with the inductive hypothesis. I've given you enough explanation and analogy, so you are good with it. Now let's move to the third step. So this is the interesting aspect, okay? So the third step, we are going to base on the second step to prove the third step, right? Because you are saying that you have a game arranged this way, right? And you are saying because of how you arrange it, if you push this and it fell, then it means that this one to what follow, right? That is your assumption. So this stage is an assumption stage. The second stage is an assumption stage. Now you are done with the assumption stage. You are coming to say that you are going to base on this assumption to say that if this one is going to fall, then this two will fall. If you add one to this, right? If you add one to this, right? So that is where you add one to the second stage, and then so with step 3, that is the inductive. That is the inductive step, right? So in that instant, as I said, we are coming to prove that n is equal to what? K plus 1, right? So here we say that n is equal to what? K plus 1. Very, very interesting, right? So if n is equal to k plus 1, now we want to prove that with the step 3, we know that that is the inductive step, right? And this step, as I said earlier, we are going to base on step 2, which is the inductive hypothesis, to prove the step 3, right? So he said that this on this, and this on this, right? You push this fell. So you are assuming that if you push this, it also fell, right? If you push this, it also fall, right? So you are assuming that this should be equal to what? K, a certain uh, variable K, okay? Now, if you assume that this should be K, then the third one too, you'll be thinking it will fall, right? So you add 1 to the K, right? So that is the third stage. So n should be equal to what? K plus 1. Okay? N is equal to what? K plus 1. So that is where you prove for this n equals k plus 1. So you have to prove that n is equal to k plus 1 was what? 4. So now, because we want to prove for that, let's go and substitute into the statement, right? So we are going to have 7 to the k plus 1 from here, right? Because we are saying that n should be what? K plus 1. So we have 7 to the k plus what? 1. So, and that is what? Because this one over here, we will not subtract it. We are sending it to the right hand side, okay? And that will be what? Equivalent to 1 modulo what? 6. As I said earlier, this is just like modulo. So this is equivalent to what? 1 modulo 6. Okay. And you know that this statement can be expressed at 7 to the k plus 1 is equal to what? 7 to the k times 7, right? Or you can equally say that 7 to the k plus 1 is equal to 7.7 to the what? K, right? So this statement is valid according to indices. Are we good with that? Now, once we know that this statement is the same as this, then now let's base on the step 2, right? We can't do this without the step 2. So we are going to use the inductive hypothesis to prove the inductive hypothesis, which is the step 2, right? So we say that Now we want to prove that 7 to the k is equivalent to 7 to the k is equivalent to 1 modulo 6. So now we want to prove that 7 to the k is equivalent to what? 1 modulo 6. Because I said we are going to base on this stage to prove this stage, right? So we assume we are going to prove that 7 to the k is equivalent to what? 1 modulo 6. Okay, so let's come up here. All right, so now that we know that we are using step 2 to prove this step, so we are saying that 7 to the k is equivalent to what? 1 mod 6. So now let's try to multiply both sides by what? 7. Okay, so we multiply both sides by multiplying both sides by 7. All right, so once we multiply both sides by 7, we are going to have 7 to the k times 7, right? And that is equal to 7 times 1 mod 6, right? And we know that 1 mod 6 in here is 7 to the power k plus 1, right? So we are going to say that 7 to the k dot, you know that this is the same as 7 to the k plus 1, right? And this is equivalent to 7 to the k plus 1, right? So this is basically telling us that 7 to the k plus 1 is equivalent to what? 1 mod 7, right? 1 mod 7. So 7 to the k plus 1 is equivalent to 1 mod 1 mod what? 6. Okay, so we're looking at this statement, it means that the assumption that we did in step 2 is entirely true, right? The assumption that we did in step 2 that 7 to the k should be what? Equivalent to what? 1 mod 6 is entirely what? True, right? So we say that hence 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 the statement is true. Hence the statement is true for n equals what? K plus 1, right? The statement is true for n is equal to what? K plus 1. So we can conclude that we can conclude that we can conclude that we can conclude that by the mathematical principle and using modulo or modular arithmetic, the statement 7 to the n minus 1, right, is entirely what? True for n belonging to what? The natural numbers n, right? So for n belonging to what? The natural numbers, right? So this is our conclusion to the problem. Now, Give me some short minutes. I'll be right back with an alternative solution to this particular one. In that case, we are not going to use the modulo, right? We are going to use our normal way or our normal understanding. This is purely abstract understanding, right? So this is modulo arithmetic um, understanding, right? And this is entirely 100% correct. So now, give me some short break. I'll be right back with an alternative way of approaching this particular problem. All right, see you. So, welcome back from the short break. I believe you have been able to glance through that particular proof or that particular approach and you are good with it. Now, let's look at this alternative way of handling this particular problem. So now we know that we are going to go through 3 steps, right? So let's go. So step 1, which is the base case. So as usual, the base case is fixed. All the steps are fixed, right? Just that this, we are now coming to use the modulo arithmetic approach, right? So the base case, we say that n should be equal to what? 1. So we are going to say that 7 to the power 1 minus 1, right? And this is equal to 6 divided by 7 minus what? 1. And this is what? 6. This minus this is 6, right? So we can say that this is true, means that the base case is true, right? So the base case is what? Entirely true. Now, as I said earlier, we are not interested to know the output of this. We just want to know if this result will be in integers, right? So this result should be found in Z, right? This result should be found in what? In Z. And you know that this dividing this, you get what? 1. And 1 is what? Is inside this, right? So you are good with that. Now let's go to the step 2, which is the inductive hypothesis, right? Where we are going to assume that the statement is true for some n is equal to what? K. So step 2, inductive hypothesis, right? Where we say that the statement is true when n is equal to what? K, right? So we are going to substitute n equals k into the statement and see something, right? So we say that 7 to the k minus 1, right? So this is what we have. And this statement, naturally, right, it means that 6, right? So like I'm trying to bring the 6 there. So 6 given that 7 to the k minus 1 means that there exists an integer, right? So this statement right here means that there exists an integer such that 7 to the k minus 1 is equal to what? 6m. So remember, if you do this assumption, right, n is equal to k, and you have written your statement nicely, right? This statement right here is telling you that is trying to give you some clue that there exists some integer, right? An integer such that this right here is equal to what? 6m. And this you are seeing here is what? A number. And the m is what? The integer we are talking about. So this right here, 7 to the k minus 1 is equal to what? 6m, right? So this we can equally say that 7 to the k is equal to what? 6m plus 1, right? We can equally say that. So this is our what? Our inductive hypothesis. This is our what? Inductive hypothesis. Now, let's go to the step 3, where we are going to base on this inductive hypothesis to prove that particular step. Right. So let's go to the step 3. So with the step 3, which is the inductive stage or the inductive step. So in this stage, we need to show that this assumption that we've done, if we add 1 to it, that statement is going to be what? True. Right? That statement is going to be true. So we are going to show that the statement will be true when we add 1 to what? The k. Right? So we want to show that, or we need to show that the statement is true when n is equal to what? K plus what? 1, right? So that is the inductive step. We are basing on inductive hypothesis to prove the inductive step. Good. So once we know that this should be equal to this, then the next thing we have to do is that we have to now come and say that if that is equal to n is equal to k plus 1, then we can say that we are going to substitute k plus 1 in place of what? The n, right? So we are going to have 6 divides 7 to the k plus 1 minus 1, right? That is very true, okay? We just substituted this in place of what? The n. So that is what we have here. Now, let's consider 7 to the k plus 1 minus 1, right? So let's consider this particular one and ignore this for now. So we are considering 7 to the k plus 1 minus 1, right? Now, we know that 7 to the k plus 1 is just indices, right? That is just indices. So we know that 7 to the k plus 1 is the same as 7 times 7 to the k minus 1, right? So this statement is valid. Are we good with that? So once we know that this statement is the same as this statement, now let's come up here. So you could see that we are not using the modulo arithmetic at this point, right? This is a nice approach as well. So let's come up here and look at something. So now what we have to do is that we have to manipulate this particular statement, right? We have to manipulate this particular statement or this expression so that we can use the inductive hypothesis, right? So you can see that this is our inductive hypothesis, right? So we have to manipulate this so that we can use this inductive hypothesis, right? So we are going to manipulate that. Now, what can we do here? What can we do? right? The only thing we can do here is to multiply through by 7, right? Is to multiply through by 7. Okay, so we have to multiply through by 7. So we are going to multiply through by 7. So 7 times 7 to the k, right? 7 times 7 to the k minus 1 is equal to 7 into 7 to the k minus 1 plus 7 minus 1, right? So we multiply through by 7. So if you multiply through by 7, you can see that 7 will multiply the whole of these brackets, right? Okay, 7 will multiply through the whole of the brackets, right? Plus 7 minus 1. So we will be having, when you expand this, right here, you can see that this will give us 6, right? So we're going to have 7 into 7 to the k minus 1 plus this will give us 6, right? This, the difference here will give us what? 6. So we're going to say that now, remember, such an interesting game. Remember that this right here is equal to 6m, right? So if that is the case, then it means that we can substitute 6m in place of what? 7 to the k minus 1, right? So we have 7 into 6m plus 7 into 6m plus 6, right? Plus 6, right? So we have 7 by 6 is basically 42. So 42m plus 6. Now, 42m plus 6, what is the most common item, or what is the common argument between these two terms, 42m and 6? The common argument between these two terms is basically 6, right? So we can factor 6 out. We can factor 6 out and then say that we have 6 out, then we have 7m plus 1. So you expand this back, you get back to what? This, right? Now, if you have 7m plus 1, okay, if you have 7m plus 1, then this clearly shows that 7 to the k plus 1 minus 1 is what? Divisible by what? 6, right? If you have this here, then this clearly shows that 7 to the k plus 1 minus 1 is divisible by 6. So this clearly shows that this clearly shows that this clearly shows that 7 to the k plus 1 minus 1 is divisible by 6. Okay, this clearly shows that 7 to the k plus 1 minus 1 is what? Divisible by what? 6. Right. So that will bring us to the end of this particular problem, and you can conclude that hence the inductive step also works. So the inductive step, which is the step 3, is also working out, because if you put m here, m, so let's say that m is what? 5. 7, 5, 35. 35 plus 1 is 36, right? So you know that 6 can go into what? 36. Are we good? So it becomes what? An integer. Okay? The result becomes an integer. Now the next number that can go is 11. You put 11 here, you have 77. 77 plus 1 is 78. And you know that 6 can go into what? 78, right? 13 times. Now you have to look at some trend, right? So you can see that if you move first, right? First one is 5. The next move should be what? The 11th one. So you can see that addition of what? 5. So this plus 5, it means that the next one will be what? 17, right? So in that order. So we can conclude that since all the steps holds, then by the mathematical induction, 6 divides 7 to the n minus 1 for all n belonging to what? The natural numbers is what? Valid. Okay, so that ends the proof of this particular problem. Okay, thank you very much for watching. I really appreciate your time. Please don't forget to subscribe, share with your mates, and I'm going to give you more updates. Bye bye.